Imagine holding a piece of rock or maybe a gemstone in your hand, and as you turn it, you see this mesmerizing dance of colors just unfurling across its surface.
Mm.
Deep blues shifting to fiery reds, then, shimmering purples all changing right before your very eyes.
Feels like magic, doesn't it?
It really does. But it's not magic, though it certainly feels like it sometimes. What you're actually witnessing is a captivating optical phenomenon called iridescence.
Right.
And today we're embarking on a journey, a deep dive really, to decode this silent, vibrant language of the Earth's hidden treasures.
It truly is one of nature's most stunning displays. It's this play of light that it kind of transcends simple color, making a surface seem almost alive.
Yeah, live is a good word for it.
And while iridescence graces, everything from a butterfly's wing to maybe a slick of oil on water, our deep dive today focuses specifically on how it manifests within minerals and gemstones. We'll be unlocking the intricate science behind these shifting hues, taking you from the famous Peacock ore all the way to the subtle, almost ethereal glow of Moonstone.
Our mission here is to reveal how understanding these unique optical properties helps us not only appreciate their inherent beauty, but also provides crucial clues for identifying, categorizing, and even understanding the geological history of minerals themselves.
Exactly. It's practical knowledge, too.
We've pulled together a really rich tapestry of sources for this deep dive, from, comprehensive geological archives and academic crystallography lectures to detailed scientific papers. So prepare to discover what truly makes these mineral marvels shimmer.
Indeed. Get ready to unveil the secrets of light interference, diffraction, and structural coloration. You'll discover how the seemingly invisible microscopic architecture within a crystal can give rise to such macroscopic wonders,
Yeah.
creating optical effects that have captivated humanity for centuries and, continue to inform our understanding of the planet.
So let's unpack this fascinating phenomenon. To truly grasp how these minerals put on such a spectacular light show, we first need to, define iridescence properly. It's also known as goniochromism, which is a bit of a mouthful, perhaps.
It is, yeah.
But it precisely describes the phenomenon where certain surfaces appear to gradually change color as either the angle of view or the angle of illumination shifts.
Right. The key is that gradual change.
It's not a static color, it's dynamic, it's alive with movement.
That's right. And the word iridescence itself has a truly beautiful and fitting origin, connecting directly to its visual essence.
Oh, yeah.
It's derived from the Greek word iris, which means rainbow, combined with the Latin suffix "escent," signifying having a tendency toward.
Oh, yeah. Okay. Iris, like the rainbow.
Exactly. And in Greek mythology, Iris was, of course, the personification of the rainbow and served as a messenger of the gods. So you can see how perfectly that name captures the essence of this shimmering visual phenomenon. It's like a color story woven from light itself.
That's a perfect linguistic fit for such a visual marvel. But how does it actually work? At a fundamental level, what's going on behind the scenes to create these shifting rainbows?
Right, because it's more than just surface shine.
Yeah, it's far more than just a simple surface sheen. The underlying mechanisms are quite intricate, but the primary cause is a fascinating process called wave interference.
Precisely, wave interference. This occurs when light waves interact with extremely fine microstructures or incredibly thin, transparent films, either within the mineral or on its surface.
Okay, so tiny structures or thin films.
Right. Imagine light striking a very thin layer. Think of a delicate, almost invisible film. Part of that light reflects immediately from the very top surface. But another part, instead of reflecting directly, actually penetrates through that film and then reflects from the bottom surface. So you've got two reflections happening.
Top and bottom.
These two reflected light waves then travel back out, and crucially, they recombine.
And here's where it gets really interesting, right? As these light waves reflect, they undergo something called phase shifts.
Yes, exactly. Phase shifts.
This means they become slightly out of sync with each other. Now, when the crests and troughs of these waves align perfectly, they amplify each other, making those specific frequencies or colors appear much brighter to our eyes.
Constructive interference.
Right, constructive interference. But when they're out of sync, say a crest from one wave might meet a trough from another, they actually cancel each other out.
Destructive interference.
Destructive interference, yeah. And it effectively attenuates or dims those particular frequencies, basically making them disappear from the spectrum we perceive.
This selective amplification or attenuation of specific light frequencies is what, modulates the incident light, allowing us to perceive different colors as the angle changes. And the thickness of these thin layers is absolutely crucial.
How crucial.
It acts like a natural prism, basically. Just a difference of a few nanometers, tiny, tiny differences in thickness, dictates the specific interference pattern we observe.
Wow, nanometers.
Think of those familiar examples. The vibrant, swirling, shifting colors you see on an oil film on a puddle after it rains.
Yeah, totally.
Or the delicate, transient rainbows dancing across the surface of a soap bubble. Those are classic, everyday examples of thin film interference producing iridescence.
Okay, so that's interference. But beyond this fascinating interplay of waves, you mentioned another key mechanism creates iridescence.
Yes, diffraction.
Diffraction, okay.
This involves the scattering of light due to precisely spaced structures, like what you'd find on, say, a diffraction grading a surface with thousands of tiny parallel grooves. When iridescence is caused by diffraction, you typically see the entire rainbow spectrum fanning out as the viewing angle changes. All the colors spread out.
Ah, so that's the difference from interference.
It is, yes. Interference might show a narrower range of colors, depending on the specific layer thicknesses involved. Diffraction often gives you the full spread.
Gotcha.
Everyday examples of diffraction-induced iridescence include, well, the effects seen on the surface of CDs and DVDs. Remember those?
Oh, yeah, definitely. The rainbows on those.
Right, where the microscopic data grooves scatter light into its constituent colors. You can also observe this in some types of prisms, or even in certain cloud formations, where ice crystals or water droplets are spaced just right to create breathtaking cloud iridescence.
Wow. Okay. And when we talk about iridescence in the natural world, these colors produced this way are often referred to as structural coloration, right?
Yes, structural coloration. That's a crucial concept because it means the color comes from the physical structure of the material itself, not from pigments or dyes.
Right, not like paint.
Exactly. And this revolutionary idea actually dates back centuries to the insightful observations of the scientist Robert Hooke back in 1665.
Hooke, from the microscope guy.
The very same. Hooke, in his seminal work Micrographia, famously examined a peacock's feather under his microscope.
Oh.
He noted that its stunning iridescence vanished completely when the feather was submerged in water, but then miraculously reappeared once it was removed and dried.
Huh. So the water made it disappear?
Temporarily, yes.
Hmm?
And this simple yet profound experiment provided compelling proof that pigments could be responsible for the color because, well, pigments wouldn't just disappear and reappear like that, would they?
No, that makes sense.
We now understand that in peacocks, this structural color is due to a complex, precisely ordered photonic crystal structure within the feathers that manipulates light in a highly sophisticated way. Tiny, tiny structures.
Amazing. Speaking of related optical effects, there's also something called pearlescence. How does that fit in?
Ah, pearlescences. It's
Yeah.
very closely akin to iridescence, caused by similar light manipulation mechanisms like interference and diffraction in thin layers.
Okay, so what's the difference then?
The key distinction with pearlescence is that some, or even most, of the reflected light is white. It gives the object that characteristic pearl-like luster, rather than a full spectrum of changing hues like you might see in, say, opal.
So it's like iridescence, but with a strong white shimmer.
Exactly. You'll often hear the term pearlescent used to describe certain paint finishes, particularly in the automotive industry. You know those car paints that shimmer?
Yeah, the fancy ones.
Right, they produce these soft iridescent effects that shimmer with a whitish undertone. So while it's definitely a cousin to iridescence, pearlescence specifically highlights that lustrous, often creamy or whitish, reflective quality that makes a natural pearl so captivating.
Okay, that clarifies it. Now that we've delved into the science, the definitions, the mechanisms, let's transition into the really dazzling part of our deep dive. Iridescence as it manifests in the mineral kingdom itself.
My favorite part.
Mine too. And when we talk about iridescent minerals, we simply have to begin with one of the most famous and visually striking, Bornite.
Absolutely.
Or, as it's more commonly known.
Peacock ore.
Exactly.
It is a fantastic starting point indeed. Bornite is a sulfide mineral. Its chemical composition is Ct5FeS4, copper, iron, sulfur.
Right.
Now, while its internal atomic structure technically places it in the orthorhombic crystal system, we'll get more into crystal systems later, it often appears pseudo-cubic in its outward form, sort of blocky or rounded.
Okay. So it looks cubic, but isn't technically.
Pretty much, yeah. And on freshly fractured surfaces, Bornite has a rather unassuming, almost dull brown to copper red color.
Yeah.
Not very peacock-like at first.
But here's where the magic and its nickname, truly comes alive, isn't it?
It is. Once it's exposed to air, its surface rapidly tarnishes.
Tarnishes, like silver does.
Similar idea, but with much more spectacular results. This natural oxidation process creates microscopically thin films of various copper oxides on its surface. And these films then transform into these incredible, vibrant, iridescent shades of blue, purple, sometimes even bronze, or a whole kaleidoscope of all three.
Wow, so the tarnish is the color.
The tarnish creates the thin films that cause the color through interference. It's this dynamic chemical interaction with the air that earns it the nickname Peacock copper or Peacock ore.
That's fascinating. It's like a living example of how mineral surfaces interact with their environment.
It really is. It offers clues to geological conditions and even weathering processes over time. But beyond its striking appearance, Bornite is also economically important,
Right, it's a copper ore.
a significant one. It contains an impressive approximately 63% copper by mass, making it a valuable resource in the mining industry.
Where do you typically find it?
Geologically, it occurs widely in porphyry copper deposits,
Yeah.
often found alongside the more common chalcopyrite, forming significant ore bodies. You can also find it disseminated or sort of scattered in mafic igneous rocks,
Okay.
in contact metamorphic skarn deposits, where hot fluids have altered surrounding rocks, in pegmatites, and even in sedimentary capriferous shales. It pops up in quite a few places.
And are there famous locations for it?
Oh, yes. Some of the most notable localities for Bornite crystals include the historically rich mining districts of Butte, Montana, and Bristol, Connecticut in the U.S. Further afield, you can find it in places like Cornwall, England, the stunning Frostnitz Alps in Austria, the Mangula mine in Zimbabwe, Nuva mine in Morocco, the rugged west coast of Tasmania, and the vast mineral fields of Jeskazgan, Kazakhstan.
Wow, it's all over the world.
Pretty much. There are even traces of it found amongst the iron-rich hematite in the Pilbara region of Western Australia, showcasing its widespread occurrence.
And its history. When was it first identified?
Historically, Bornite was first meticulously described way back in 1725. It was identified from an occurrence in the Ore Mountains of Bohemia, an area now part of the Czech Republic, which is renowned for its mineral wealth.
Okay.
It was later formally named in 1845, honoring the Austrian mineralogist Ignaz von Born, who contributed significantly to the study of minerals.
Ignaz von Born. Got it. So what's the deeper science behind Bornite's spectacular dynamic sheen beyond just the surface tarnish creating those oxide films?
Right, because there's more to it. It's intrinsically linked to its internal structure and how that structure actually changes with temperature.
Oh, interesting. How so?
At temperatures above 228 degrees Celsius, that's 442 Fahrenheit, Bornite actually has an isometric or cubic structure internally.
Okay, so hot Bornite is cubic.
Essentially, yes. At that temperature, its atomic framework is based on cubic, close-packed sulfur atoms, with the copper and iron atoms just randomly distributed within those spaces. It's a bit disordered.
Right.
But here's the crucial part, the key to its optical properties. Upon cooling below that critical temperature of 228 degrees C, the iron and copper atoms don't just stay random. They order themselves.
They line up.
Into distinct organized patterns, yes. This ordering process actually reduces the crystal's symmetry from isometric down to orthorhombic, creating a more complex, layered internal architecture.
Ah, so the cooling changes its fundamental symmetry.
Exactly. And this shift in ordering and the resulting internal structure, coupled with those thin films of oxidation on its surface, are absolutely key to the optical phenomena and the iridescence we observe. It's a combination effect.
Fascinating.
Furthermore, Bornite's composition isn't rigidly fixed either. It can vary significantly in its copper and iron content, forming what we call solid solutions with related minerals, like chalcopyrite and digenite.
Meaning it's like a blend.
Kind of, yeah. And it's also very common to find tiny blebs and lamellae, which are just microscopic separations, forming distinct tiny blobs and thin layers of these other minerals exsolving or separating out within the Bornite as it cools.
Like tiny inclusions.
Exactly. And these contribute significantly to its unique visual effect by creating additional layers for light to interact with, more surfaces for interference.
So it's complex both chemically and structurally.
Very much so. And while you often find Bornite in a massive, kind of unformed state in deposits, rare individual crystals can indeed be found. Sometimes they exhibit cubic, dodecahedral, or even octahedral shapes. And fascinatingly, these crystals sometimes display something called penetration twinning.
Twinning. What's that?
That's where two separate crystals intergrow in a symmetrical, often interlocking fashion, creating even more complex forms. It's another layer of structural complexity.
Okay. Bornite is clearly amazing, but moving beyond that striking example, the mineral kingdom offers a whole rich palette of other dazzling iridescent gemstones, doesn't it?
Oh, absolutely. Each with its own unique and fascinating mechanism for producing that captivating play of color.
Right. Let's start with Opal, often hailed as the queen of gemstones for its iridescence, or more specifically, its play of colors.
Yes, Opal's play of color is legendary.
And unlike Bornite's surface tarnish, Opal's renowned iridescence isn't due to a chemical reaction on its surface, right? It's something internal.
That's exactly right. It's all about its truly unique internal structure. And the colors can range from fiery reds and oranges to calming blues and greens, all shifting within a single stone.
So what is that structure?
Opal is essentially composed of countless, tiny, uniformly sized silica spheres. Think microscopic billiard balls,
Okay.
typically around 0.3 micrometers in diameter, and they're meticulously stacked in a regular three-dimensional array. Like oranges stacked at the grocery store, but way, way smaller, more ordered.
Right.
When white light enters the opal, these precisely arranged spheres act as a natural diffraction grating, scattering the light.
Ah, diffraction again.
Yes, primarily diffraction in opal's case. If these spheres have similar diameters that are grouped in layers, they cause light waves to interfere with each other after diffracting, producing the vibrant flashes of color we admire.
So the size and stacking are key.
Absolutely. Common opals, the ones that look milky or glassy but don't have that fire, they lack iridescence because their silica spheres are generally either too large, too small, or just too chaotically dispersed to create this ordered diffraction effect. The regular stacking is missing.
Makes sense. And Australian opals are particularly famous.
Oh yes, especially the prized black opals from Lightning Ridge. They're among the most famous and highly sought after in the world, known for their exceptional vibrancy against that dark background.
Right.
Ethiopian opals have also gained significant popularity more recently. They often show vivid play of colors, and many are hydrophanous.
Hydrophanous. What's that mean?
It means they can absorb water, and sometimes their appearance changes when they do. It's quite interesting. But yeah, the play of color in opal is truly a wonder of natural nanoengineering.
Definitely sounds like it. Okay, then there's Moonstone, which you mentioned has a more subtle, almost ethereal elegance.
Yes, Moonstone. It's a feldspar mineral, and it exhibits a phenomenon known as adulorescence.
Adulorescence, another great word.
Isn't it? It describes this captivating optical effect where a billowy, sort of internal light appears to glide across its surface. It creates this captivating play of blue or white hues, really reminiscent of moonlight or maybe clouds drifting across a full moon.
It does have that soft glow. How does that work?
Well, this ethereal effect isn't a surface phenomenon either. It's due to alternating intergrown layers of two different feldspar minerals, albite and orthoclase, inside the stone.
Ah, internal layers again?
Yes, thin layers scattering light in a very specific way. Because these layers are incredibly thin and parallel, light enters and scatters differently based on the viewing angle, giving that moving sheen.
So it's more subtle than opal?
Generally, yes. Its iridescence, or adulorescence, is often dominated by shorter wavelengths of light, giving it that characteristic blue glow. And it's also compounded by light scattering from tiny internal particles, adding to the softness.
Okay. And speaking of feldspars, that brings us to Labradorite. Truly nature's canvas of color, wouldn't you say?
Oh, absolutely. Labradorite is spectacular. It's known for its incredibly vibrant, almost metallic flashes of blue, green, gold, and sometimes even violet and copper.
In a phenomenon called labradorescence.
Precisely, labradorescence. This spectacular play of color is caused by the interference of light due to its complex internal lamellar structures, those thin layers again.
When you turn a piece of labradorite, it's like a flash of pure magic just emerging from within the stone.
It really is. And the science behind labradorite's iridescence is particularly fascinating. This is where we really get into the intricacies of crystallography.
Okay, let's get intricate.
So labradorite is a triclinic feldspar. Now, triclinic means its three crystal axes are all unequal in length and are inclined to each other, giving it a pretty low degree of symmetry compared to, say, a cubic crystal.
Right, less symmetrical.
Chemically, it's a solid solution, basically a mixture of albite and anorthite, but with a significant proportion of potash feldspar, or orthoclase, mixed in.
Okay.
Now, crucially, studies by people like Raman and Joryaman show that common impurities like iron, oxygen, or magnesium are not the cause of its characteristic iridescence. That was a common misconception.
Oh, so it's not impurities. What is it then?
Instead, the iridescence is hypothesized to arise from the extremely fine-scale segregation separation of that monoclinic potash feldspar, the orthoclase, into tiny crystallites or lamellae, those microscopic thin layers we keep mentioning, embedded within the main triclinic albidonorthite matrix.
So tiny layers of one feldspar inside another?
Essentially, yes. And because there's a significant difference in the refractive index, how much light bends between these orthoclase components and the surrounding matrix, the crystal becomes optically heterogeneous.
Meaning light behaves differently in different tiny parts.
Exactly. Light interacts differently as it travels through different parts of the structure, causing it to interfere and reflect in that dazzling way. What's truly remarkable is that despite being optically distinct, the orthoclase and the albidonorthite structures are crystallographically coherent.
Coherent.
Meaning their crystal axes are coincident, or nearly so. They line up, allowing them to grow together seamlessly at a microscopic level, even though they're slightly different.
Wow, that's complex.
It gets even more remarkable when you consider twinning.
Twinning again, like in Bornite.
Yes, but even more critical here, Labradorite frequently exhibits multiple twinning, like the albite or paracline types, where the crystal structures on either side of a composition plane are mirror images of each other, creating these repeating patterns.
Okay.
And here's the key insight from Ram and J. Arman. The very lamellae, the tiny layers responsible for the iridescence, also meticulously follow this twinning pattern.
So the layers in the twinning are linked.
Intimately linked. And this fascinating structural arrangement means that a single specimen of labradorite will actually display iridescence in two distinct settings when the light source and viewing angle are fixed.
Two flashes at once.
From different parts of the twin crystal, yes. But remarkably, they display identical colors.
Whoa.
Geometrically, the settings for these two reflections are precisely related to the internal twinning planes. For example, maximum intensity often occurs at about 14-degree angles from certain crystal planes. It's a very specific, predictable phenomenon based on the structure.
That is incredibly precise.
And experiments conducted with polarized light further confirm this intricate model. They show that the reflected light is completely polarized in a direction transverse to the incident beam, providing strong evidence for this lamellar structure and twinning being the source.
Okay, what about the colors themselves? Is it like the oiled, slick interference?
Well, yes and no. When we examine the spectral characteristics of Labradorite's iridescence, it's distinctly different from a simple thin film effect, like Newton's rings, which would show alternating dark and bright bands in the spectrum, or only faint first-order colors.
How is Labradorite different?
Labradorite exhibits a continuous variation of intensity. It often starts with a rich, vibrant blue, far more intense than any faint first-order blue, followed by other rich colors like green and gold as the angle shifts. It doesn't have those simple bands.
Why the difference? Why so rich?
This is explained by the earliest stage of segregation, where the orthoclase forms incredibly small crystallites first. These tiny particles cause a phenomenon known as the Tyndall effect.
Tyndall effect? Like why the sky is blue?
Exactly like that. Much like the way dust motes scatter sunlight in a beam, these tiny crystallites preferentially scatter shorter wavelengths of light blue light, which predominantly gives rise to those vibrant blue hues we see first.
Ah.
Then, as segregation progresses, these crystallites grow into larger, more defined lamellae, the layers. These layers then become large enough to produce specific colors based on their thickness through interference, but they exceed the dimensions that would produce only those simpler, first-order Newtonian colors, hence the full, rich spectrum.
So it starts with scattering for the blue, then interference from bigger layers for the other colors.
That's the current thinking, yes.
Yeah.
The combination effect that evolves as the structures form. It's also quite noteworthy that the angular spread of the reflected light, how wide the flash appears, is greatest for blue iridescence.
Oh, really?
Yeah, appears about twice as wide compared to red or orange flashes. Blue also tends to remain visible longer as you turn the specimen.
Which explains why those brilliant blue flashes are so prominent and persistent in Labradorite.
Exactly. It often dominates its labradorescence.
Mind-blowing stuff.
Okay.
Beyond these remarkable feldspars, let's turn to pearl, the ocean's own luminescent treasure.
Oh, pearls. Truly unique. Their iridescence, famously known as orient, comes from layers of an organic-inorganic composite material called nacre.
Nacre, right, mother of pearl.
Exactly. Nacre is comprised of incredibly thin, overlapping, platy layers of aragonite, which is a form of calcium carbonate all cemented together by an organic protein, like a natural glue.
And these layers form around?
Around an irritant, like a grain of sand, within an oyster or mollusk. layer upon layer upon layer.
So how does the orient, the iridescence, happen there?
The orient of a pearl is created as light reflects from these thousands of regularly spaced microscopic layers of nacre, but it also diffracts from the even finer, regularly spaced crystal boundaries within those layers,
So reflection and diffraction.
both playing a role. This intricate layered structure creates the subtle, moving, almost ethereal colors we see, giving the pearl its characteristic soft glow and shifting hues. It's distinct from the vibrant flashes of gemstones like opal or labradorite. Much softer.
It is a very different look. This optical effect has made pearls prized treasures for millennia.
Absolutely, not just for their beauty, but for their unique, natural origin, built by a living creature.
Incredible. And then we have sunstone, which you said gives a glimpse of sunlight captured within a crystal.
Yes, sunstone. Another feldspar, but with a different trick up its sleeve. It doesn't display iridescence in the same way as opal or labradorite, but rather aventurescence.
Aventurescence. Okay, what's that?
It's a dazzling, sparkling effect, and it's caused by light reflecting off tiny, platy inclusions of other minerals, most commonly hematite or goethite, embedded within the feldspar matrix.
So little flakes inside.
Exactly. These inclusions act like tiny mirrors, scattering light and resembling golden, coppery, or sometimes reddish glitter suspended within the stone.
Like glitter, yeah.
The specific color and intensity of sunstone's aventurescence depend on the size, density, and composition of these metallic inclusions. Oregon sunstone, for instance, is highly prized for its exceptional clarity and the wide range of colors its aventurescence can produce, from a soft peach or pink to intense reds and coppery tones.
Oh, nice.
It often exhibits a beautiful Schiller effect, too, that appears to glow from within. It's a wonderful example of how even opaque inclusions can create a stunning optical effect.
Definitely. Okay, finally, for a truly striking and maybe surprising example, synthetic bismuth.
Ah, yes, the lab-grown rainbows.
The familiar clusters of metallic hopper crystals you often see at mineral shows with their incredibly vibrant, almost otherworldly colors, cyan, green, gold, magenta, deep blues. They are synthetic bismuth grown in a lab, right?
That's correct. They are aesthetic. And while the pure bismuth metal itself is a rather unassuming silver-white with maybe a hint of pink, its astonishing iridescent colors are not from the metal itself.
Wait, really? Not from the bismuth?
Not directly from the bulk metal, no. That's a crucial distinction. The vibrant iridescence is caused by microscopically thin surface films of bismuth oxide.
Bauxite films again, like on Bornite.
Exactly like on Bornite, but formed during the cooling process in the lab. These films form as the molten bismuth slowly solidifies and reacts with atmospheric oxygen.
Ah, okay.
The thickness of these oxide films varies minutely across the surface, creating the thin film interference that produces the spectacular rainbow effect we see.
And what about that weird shape? The stepped cubes.
That distinctive hopper crystal shape, which looks like a stepped, hollowed-out cube, is a pseudo-cubic habit resulting from this very specific slow cooling process. The edges of the crystal grow faster than the faces, creating that unique, geometric, almost alien-looking structure.
Fascinating. So it's a chemical interaction at the surface, rather than a deep structural property of the metal itself that creates that brilliant display.
Precisely. A surface effect driven by chemistry and thin film physics.
Wow. Okay, so we've covered iridescence in quite some depth, exploring its various manifestations in minerals. But it's important now to distinguish it from another fascinating optical phenomenon that also involves a change in color: pleochroism.
Yes, absolutely crucial. People often confuse them, but they are fundamentally different.
Right. While both involve a visual transformation, they have different causes and appearances. So, what is pleochroism?
Pleochroism refers to a mineral or gemstone displaying two or sometimes three distinct colors when viewed from different angles, specifically when viewed along different crystallographic axes.
Okay, distinct colors, not a gradual shift, and viewed along specific internal directions.
Exactly. This effect is intrinsic to the crystal's internal atomic structure and how light interacts as it travels through it, not from surface films, inclusions, or interference like iridescence. It's about how the crystal absorbs light differently depending on the direction light passes through its atomic lattice.
So iridescence is often reflection diffraction from layers or surfaces, while pleochroism is about absorption through the crystal structure.
That's a great way to put it, yes. And unlike iridescence, which you can see easily with the naked eye just by moving the light of the stone, pleochroism, while often visible, is typically enhanced and more clearly observed with specialized tools.
Like what?
Like polarized light or a dichroscope, which isolates light vibrating in different directions. Although you're right, for many strongly pleochroic gems, you can absolutely see the color change just by rotating the stone in your hand.
Can you give some examples?
Sure, classic examples really highlight this distinct effect. Take tourmaline. A pink tourmaline, for instance, might appear a paler, delicate pink when viewed along its AD axis, but then transform into a much more intense, saturated pink when viewed along its main C axis. Two distinct pinks.
Okay.
Another excellent example is blue sapphire. It often shows that rich, deep blue when viewed looking straight down into the table of the stone. But it can appear a distinct greenish blue or even quite green when viewed from the side because many blue sapphires actually exhibit a green absorption component along their AD axis due to their iron and titanium content.
So the blue we see face up is one direction, the green is another.
Precisely. We also see dramatic pleochroism in iolite. It's sometimes called water sapphire, precisely because of its striking trichroism.
Trichroism, 3 colors.
Yes, displaying 3 distinct colors. It can range from a vibrant blue-violet to a yellowish gray, and then to a clear light blue, all depending on the angle you view it from. It's quite remarkable.
Wow.
And tanzanite is another famous example. Naturally, before heating, it exhibits 3 distinct colors, often blue, violet, and kind of reddish-brown or bronze. Though this trichroism is usually reduced to a more vivid blue-violet dichroism 2 colors after heat treatment, which is very common for tanzanite.
Okay, so heating changes the pleochroism too.
It can, yes, by altering the crystal structure or the state of the color-causing elements slightly.
So let's summarize the key differences clearly then. Iridescence.
With iridescence, the colors gradually change as the angle of observation or illumination shifts, like a flowing rainbow.
Right. And it's caused by interference or diffraction from microstructures, thin films, or inclusions, and you see it without needing special filters.
Exactly. It's a continuous flowing change, often related to reflection or scattering from structured surfaces or layers.
Conversely, pleochroism.
With pleochroism, the colors are distinct and depend on the specific crystallographic direction you're looking through the stone.
Right. It's an internal property related to the crystal's atomic structure and how it absorbs light differently along various axes.
Precisely. And while often observed and enhanced with polarized light, for many striking examples, it's not strictly necessary. The key is you're seeing 2 or 3 specific different colors, not a smooth gradient.
Got it. That distinction is really helpful. And it brings us nicely to an even deeper dive, doesn't it, into what fundamentally gives minerals their unique properties, including how they interact with light in these ways, their atomic structure, and the whole concept of crystal systems and symmetry.
Yes, this is the bedrock, the foundation. It's essentially the invisible blueprint of minerals, dictating everything from their external shape to their optical behaviors like iridescence and pleochroism.
So every mineral possesses a specific, highly ordered internal arrangement of atoms. That's what makes it a crystal, right?
Correct. And that precise arrangement dictates everything. Its hardness, how it breaks cleavage, its density, and absolutely how it interacts with light.
And to describe this internal order, scientists use crystallographic axes.
Yes, these are imaginary lines we use as references to describe the geometric symmetry and form of a crystal. Think of them like X, Y, and Z axes, but specific to the crystal's structure.
Okay.
These axes can be orthogonal, meaning at perfect 90-degree angles to each other, like in a cube. Or they can be skewed, intersecting at other angles. And depending on the crystal system, there can be 3, 4, or even 6 of these axes forming a reference set.
And within these atomic arrangements, crystals possess various elements of symmetry.
Exactly. Symmetry is key to understanding crystal structure. A plane of symmetry is like a mirror plane. It perfectly divides a crystal into 2 identical halves that are mirror images.
Okay, mirror plane.
Then there are axes of symmetry. If you rotate a crystal around one of these axes, identical physical appearances will repeat at discrete, regular angles.
Like spinning it.
Right. This could be binary symmetry, where the appearance repeats every 180 degrees. Trigonal symmetry, repeating every 120 degrees. Tetragonal symmetry every 90 degrees. Or hexagonal symmetry, repeating every 60 degrees. It depends on the crystal's internal order.
Makes sense.
And lastly, there's often a center of symmetry. This means if you imagine a line passing from any point on the crystal surface through its exact center and out to the opposite side, you'll find an identical point. In simpler terms, opposite faces across the center are identical in orientation and geometry.
So mirror planes, rotation axes, center of symmetry.
Yes, and it's important to note that a crystal can have various combinations of these symmetries. It might possess axes of symmetry, but no planes, or vice versa. It demonstrates the incredibly diverse complexity of these fundamental structures.
And all minerals are categorized based on these symmetries and axes?
Precisely. They're meticulously categorized into one of 7 crystal systems based on their unique crystallographic axes and symmetry elements. It forms a precise hierarchy of structure, from most symmetrical to least symmetrical.
Okay, what are the 7 systems?
The simplest and most symmetrical is the isometric or cubic system. Here, all 3 axes are equal in length and are perfectly orthogonal at 90 degrees.
Like a perfect cube.
Exactly. They exhibit a minimum high symmetry that includes multiple 3-fold and 2-fold axes, plus a center of symmetry. These crystals typically form highly closed shapes like cubes, octahedrons, or dodecahedrons, things that look balanced from all sides.
And examples?
Classic examples include halite, which is a common rock salt, the magnificent diamond, pyrite with its distinct metallic cubes, and galena.
And bornite. You said it looked cubic, but was actually...
Orthorhombic at lower temperatures.
Right.
While it often appears pseudo-cubic due to its external form, its internal atomic ordering below 228 degrees C puts it technically into the orthorhombic system. This really highlights how complex these classifications can be and how internal atomic changes directly impact the classification and the properties.
Okay, so isometric is the most symmetrical. What's next?
Next, we have the tetragonal system. In this system, one axis is either longer or shorter than the other two, but all 3 axes remain perfectly orthogonal at 90 degrees. Think of stretching or squashing a cube along one direction.
Right.
Their symmetry is lower than cubic, usually possessing a single 4-fold axis of symmetry. Forms can be closed, like zircon, which often forms distinct pyramids at both ends, or open, like a simple column, or a column closed only at one end. Prominent examples include zircon and chalcopyrite.
Okay. Then orthorhombic, where bornite fits.
Yes, orthorhombic. Here, all 3 axes are unequal in length. But crucially, all are still perfectly orthogonal to each other, intersecting at 90-degree angles. Think of a rectangular box, like a shoebox, where all sides are different lengths, but all corners are right angles.
Got it.
This system requires at least one 2-fold symmetry axis. Like tetragonal crystals, their forms can be open or closed. Barite, with its distinctive tabular crystals or rose formations, is a common example. And bornite, as we keep mentioning, crystallizes in this system when it cools, showcasing how its unique internal structure fits this classification.
3 down. What's next? Hexagonal.
Hexagonal system, yes. As the name implies, it features characteristic 6-fold symmetry, or sometimes 3-fold symmetry, referred to a hexagonal axis setup. This system technically requires 4 crystallographic axes for description, 1 main vertical axis, and 3 horizontal axes in a plane perpendicular to the main axis, inclined at 120 degrees to each other, or 60 degrees between adjacent ones.
4 axes. Okay.
They must possess at least 1 6-fold or 3-fold symmetry axis related to that vertical axis. Beryl, the mineral group that includes emerald and aquamarine, is a classic example, often forming beautiful 6-sided prismatic crystals.
Beautiful. And trigonal.
Trigonal system is very closely related to hexagonal, sometimes considered a subdivision. It also uses 4 axes for description in the same orientation. The key difference is they specifically require only 1 3-fold symmetry axis as their highest symmetry along the main vertical axis.
Okay, 3-fold symmetry.
Examples here include tourmaline, which often forms distinctive open crystal structures with triangular cross-sections, and dolomite, a common carbonate mineral, and also quartz.
Right. 2 more systems left?
Yes, the lower symmetry ones. Next is the monoclinic system. Here, mono means 1, and clinic means inclined.
1 inclined axis.
Exactly. This means 1 crystallographic axis is skewed, or not at a 90-degree angle, to the plane containing the other 2, while those other 2 might be orthogonal or also skewed depending on convention, but there's always that 1 inclined relationship. The specific symmetry is lower, often just a single 2-fold axis or a single mirror plane.
Okay.
They can form open or closed habits. Common examples include gypsum, known for its soft, often platy crystals, and orthoclase, the common feldspar we mentioned earlier in relation to Moonstone and Labradorite.
Ah, orthoclase is monoclinic. Okay. And finally?
Finally, we arrive at the triclinic system. Tri means 3, and clinic again means inclined.
So all 3 axes are inclined?
Pretty much. All 3 axes are skewed relative to each other, and they are all unequal in length. These crystals exhibit the lowest possible degree of symmetry. They have no planes of symmetry, no axes of symmetry, other than a 1-fold axis, which is trivial, and usually no center of symmetry either. They're fundamentally asymmetric internally.
Wow, 0 symmetry.
Essentially, yes. Their forms are typically open and often appear quite asymmetric visually. A very common example is the plagioclase feldspar series, which includes albite and anorthite.
And Labradorite.
And labradorite, yes. The feldspar, with its complex internal lamellar structures that create labradorescence, fits into this least symmetrical triclinic system.
It beautifully showcases how even the most asymmetrical crystal structures can host the most incredible light shows.
Really does. It proves that complexity, even asymmetry, can indeed be the source of stunning beauty and fascinating physics.
Okay, so that's the 7 systems, the structural blueprints. Beyond their forms and symmetries, the optical properties of minerals in the visible spectrum are also absolutely crucial for identification and understanding their light play, aren't they?
Oh, absolutely. How a mineral interacts with light is one of its defining characteristics. Transparency, for instance, just tells us how light passes through.
Right, like transparent, translucent, opaque.
Exactly. A mineral can be transparent, allowing light to pass easily and clearly, like looking through clear quartz or glass. It can be translucent, where light passes through but is scattered, so you can't see clearly through it like frosted glass or chalcedony. Or it can be opaque, completely blocking all light from passing through, like pyrite or galena.
And this can vary.
It can. Sometimes it even depends on the light's wavelength. Some minerals might be opaque to visible light, but transparent to X-rays, which is how we can image their internal structures.
Ah.
Tourmaline is a fascinating example we touched on with pleochroism. Its transparency, or rather its ability to transmit light, depends on the direction of the light's polarization relative to the crystal's axis.
The natural Polaroid filter effect.
Exactly. This is why certain types of tourmaline are used in optical instruments, because they allow polarized light to pass through mainly along its longer crystal axis.
Okay, what about other optical properties? Brilliance, fire.
Yes. That relates to dispersion and total internal reflection. As we know from basic physics, the refractive index, that measure of how much light bends when entering a material, is actually a function of the light's wavelength. Different colors bend at slightly different angles.
Like a prism-splitting light.
Precisely.
Yeah.
This phenomenon, known as dispersion, gives rise to the fire or brilliance most famously seen in diamonds. White light entering the diamond is split into its spectral colors as it passes through the faceted gem.
And it sparkles so much because
of total internal reflection. The facets are cut at angles that trap the light inside, causing it to bounce around internally multiple times before it exits, maximizing the dispersion and sparkle we see.
clever cutting. Now, here's where it gets really interesting again for our discussion of light phenomena. Double refraction, or birefringence, I mentioned it earlier.
Yes, birefringence, a truly fascinating property. It occurs when light passes through an anisotropic mineral,
Anisotropic, meaning
one that is not uniform in all directions. Optically speaking, it has different properties depending on the direction light travels through it. Essentially, anything not in the isometric cubic system is anisotropic.
Okay, so what happens in these anisotropic minerals?
The light actually splits into 2 separate rays upon entering. Each ray travels at a slightly different speed and is polarized in a different plane, vibrating perpendicular to each other.
2 rays from 1.
Yes. However, there's a catch. If the light ray happens to be aligned exactly along a specific optical axis of the crystal, there's no birefringence. The light travels as a single ray along that special direction.
Ah, the optical axis. And how does this connect back to the crystal system?
Perfectly. Isometric crystals, because they are highly symmetrical and optically uniform in all directions, isotropic, exhibit no birefringence. Light travels at the same speed, no matter the direction.
Okay, cubic means no splitting.
Right. Hexagonal and tetragonal crystals, which have that one main unique axis, are called uniaxial. They have one optical axis. Light will split into 2 rays unless it travels exactly along that single axis.
One optical axis for hexagonal and tetragonal. Makes sense.
But orthorhombic, monoclinic, and triclinic crystals, which are less symmetrical, are biaxial. They have 2 optical axes, and these axes are generally skewed relative to the crystallographic axes and each other.
2 optical axes for the less symmetrical systems.
Correct. And a classic visual demonstration of this dramatic effect is placing an object, like a dot or a line on paper, under a clear calcite crystal, especially the variety called Iceland spar.
What happens?
You clearly see the image splitting into 2 distinct displaced images. It's a direct, undeniable visual demonstration of birefringence in action. The light splits, and you see double.
That's a cool party trick.
It's fundamental mineral optics.
Right. So to truly peer into the atomic structure itself, beyond what we see with visible light, scientists need other tools, right? Like X-ray diffraction.
Exactly. XRD, or X-ray diffraction, is an incredibly powerful analytical technique used to identify minerals by analyzing their fundamental atomic structure.
How does it work? What's the principle?
The principle is quite clever and elegant. You take a sample of the mineral, usually ground into a fine powder to ensure all crystal orientations are present, and you direct a beam of X-rays at it.
Okay, shoot X-rays at powder.
Yep. Now, due to the incredibly regular, repetitive pattern of atoms arranged in the crystal lattice, that precise atomic blueprint we discussed with crystal systems, these X-rays don't just pass through or scatter randomly. They scatter in very specific directions determined by the spacing of the atoms.
Ah, the regular pattern interacts with the X-rays.
Precisely. And what's crucial is that these scattered X-ray waves then constructively or destructively interfere with each other, much like the visible light waves in iridescence. But now we're talking about interactions at the atomic scale dictated by Bragg's law.
So interference patterns from X-rays.
Exactly. This interference amplifies certain signals, constructive interference, at specific angles, while canceling out others, destructive interference, creating a distinct diffraction pattern. The resulting pattern of constructive interference peaks is absolutely unique to each mineral.
Like a fingerprint.
Exactly like an atomic fingerprint. It allows scientists to identify the mineral with incredible precision, telling us not just what elements are present, but exactly how they are arranged in that specific crystal structure.
How is it measured?
The instrumentation for X-ray diffraction typically involves an X-ray source that generates the beam, the powdered sample held in a specific position, and a movable detector or receiver that precisely measures the intensity of the scattered X-rays at many different angles relative to the incident beam.
Okay.
When you plot that measured intensity against the angle often referred to as 2, the theta, you get a distinct pattern of sharp peaks. Each peak corresponds to a specific set of atomic planes within the crystal lattice, satisfying the conditions for constructive interference.
And different minerals have different peaks.
Completely different patterns of peaks at different angles and intensities. For instance, the common clay mineral Montmorillonite shows a very characteristic strong peak signal near 12 degrees 2, using typical copper X-ray sources. Quartz has its own unique set of peaks, halites another, and so on.
So you just compare the pattern.
By comparing a sample's unique XRD pattern to vast databases of known mineral standards, scientists can achieve precise mineral identification. It's like matching the fingerprint to a database. This isn't just for identification, though. It's fundamental to understanding how minerals form, how they might change under different pressures and temperatures, how they might weather, and even predicting their physical and optical properties based on that atomic arrangement.
It really is reading the atomic blueprint.
It absolutely is. It's a testament to how deeply the invisible world of atoms dictates the dazzling macroscopic wonders like iridescence that we see and appreciate.
Wow. We've truly embarked on a profound deep dive today, haven't we? I feel like my head is full of shifting colors and crystal lattices.
Mine too. It's a lot to cover, but so fascinating.
From the mesmerizing dance of colors on Peacock ore, born from just a whisper of oxidation on the surface, to the detailed crystallography that dictates a gemstone's hidden symmetry and its unique interaction with light, whether it's iridescence, pleochroism, or birefringence.
We've really unpacked how these phenomena are not just visually stunning, but actually crucial clues to a mineral's identity and its very atomic architecture.
It's incredible to think that such vibrant beauty often stems from the precise arrangement of atoms and the way light waves interact with them, or even from those microscopically thin, invisible films of oxides forming on a surface.
These seemingly simple interactions, governed by physics, give rise to some of the most captivating displays in the natural world. And they allow us to read the Earth's history recorded in the minerals.
Indeed. It reveals that the true magic perhaps isn't in some ethereal force, but in the elegant, precise laws of physics governing light and matter.
And these properties aren't just for appreciation. As we said, they are the very tools geologists and gemologists use daily to classify, understand, and even predict the behavior of the treasures hidden within the Earth.
So a final thought for you, our listener. The next time you encounter a shimmering rock, maybe a sparkling gem, or even just an iridescent oil slick on a rainy street.
Pause for a moment.
Yeah, pause. Consider the silent story it tells, the invisible architecture hidden within, and the way light reveals it all. What hidden light phenomena or structural secrets might it be holding?
Secrets just waiting for a change in angle, perhaps a closer look with a lens or maybe even an X-ray to reveal its true, fascinating nature.
The world of minerals is always revealing new wonders, if you know how to look.
And hopefully now, you have a deeper understanding of how these brilliant plays of light truly come to life.